Am I recording? Okay.
I think so.
Wonderful. All right. All right. There was some glitch this morning in WebEx, but I think we are on board. Everyone is on board. I think so. It's good to start. I'm glad we can start on time. All right. Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed. So please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me introduce our speaker today. It is an honor to host Dr. Alice Cicirello, who is an associate professor at TU Delft. Alice is the founder and the head of the Data, Vibration, and Uncertainty Group, and currently leading the MVU laboratory at TU Delft. Alice joined the Engineering Structures Department at TU Delft in January 2020. Previous to this position, she was a departmental lecturer in dynamics and vibration at the Oxford Engineering Science Department and a career development fellow in engineering science at Balliol College from 2017 to 2019. Her research interests span from fundamental to applied research. Her technical expertise covers uncertainty quantification and machine learning, physics-based modeling, and dynamic experimental testing and their combination. Alice's research aims at developing effective strategies for supporting decisions in operating conditions and at the design stage under deep uncertainties. Alice is holding currently many positions. She is a head of the mechanics and the physics of structural section at TU Delft, and also collaborating staff within the offshore engineering section, and visiting fellow at the engineering science department at the University of the Oxford, an honorary lecturer at the Institute for Risk and Uncertainty, Department of Civil Engineering and Industrial Design at University of Liverpool, and also a member of the organizing committee of the 10th International Conference on Modern Practice in Stress and Vibration Analysis. And lastly, the member of the International Technical Committee of the 8th the International Symposium on Reliability Engineering and Risk Management. All right. Today, Alice will give a talk about the very interesting topic, which is the interpretable, explainable, and non-intrusive uncertainty propagations through expensive to evaluate models via ML optimization. Please expect a wonderful talk from Alice and enjoy it. Now, without further ado, let me pass the baton to Alice by asking our usual question. What is your favorite things to do other than research, Alice?
My favorite thing to do is listening to music while working or walking. Either
okay.
way.
What kind of music? The classical music?
I like terrible music, pop music, you know, everything that you can think of, but also jazz. It depends on the mood, you know.
It depends on the mood. Yes, yes, yes. That's how it goes. Okay, the stage is yours, Alice.
Thank you so much. Thank you so much for this very generous introduction and for having me today. It's actually my honor really to be here and to see so many of you online attending this talk. So what I'm going to talk about during this talk are actually three parts. First of all, I will tell you why should we care about the fact that we want interpretable, explainable, and non-intrusive uncertainty propagation. And then I will try to describe to you which are the most pressing challenges. And finally, I will be talking to you about how we can exploit machine learning to select the minimum number of physics-based models to run in order to get performance bounds. Okay, so without further ado, I'm going to start making strong case of why we need this. So first of all, I'm interested in engineering structure in general and engineering system. And there we have performance that we have to satisfy and that we have to meet. And of course, we have uncertainties that we have to deal with. You can imagine about the noise, vibration, and harshness performance of cars and about the sound pressure level at the drive year location. You can think about safety during launching. You can think about cost in drilling application. And you can think about other performance metric like optical data accuracy. And when we think about this kind of performance, we have to think about the things that we know and we don't know. And of course, we have to remember that if we consider just a car, just a drilling tool, just a satellite, their response will be different because of uncertainties. And these uncertainties may come from inherent variability or may come by the fact that we don't know everything about it, or we don't know all the things that we needed for our physics-based model. So uncertainty is very important. And if we think about the models that we usually run in engineering, we think about deterministic models and then how to implement uncertainties. But why is this important? Because we have to make this decision and under uncertainties. And you can think about it this very simply. You can think about the effect of uncertainties and how it will influence performance metric. So you see on the right, on the x-axis, uncertainties going from low to high, and on the y-axis, the influence on performance metric. And what we can see immediately is that if you are in the low uncertainty range, but the influence is also low, we should not worry. We can still use pretty much a deterministic model. And even if the uncertainty is very high, but we are still seeing no influence of those uncertain parameters on our performance, in principle, we can still use a deterministic model. However, the region in which we should not worry is actually really small. And most of the time, we are actually in this top corner in which we are worrying. And we are worrying for two reasons. Because in principle, if we are in the region in which there's an high influence on the performance metric of uncertainties, we rather want to change the design, or we want to gather more information. And in that case, then we want to quantify these uncertainties. We want to see the, because maybe we cannot change the design. And most of the time we are in this top part, and we want to select design that satisfy performance metric. Okay, but where are these uncertainties coming from? I told you generally they can be aleatoric or epistemic. In principle, we can think about two things. We usually use a physics-based model, and therefore we can have uncertainty related to the computational model itself. But also we have the inputs of the computational model. So if we think about the computational model, it depends on the complexity of the physics that we are currently embedding, but also the knowledge on the model parameters, so the input parameters that we are giving. Of course, then if we think about the inputs, we will have the loading condition and the manufacturing variability. The loading will arise because we will have varying environmental condition, but also operating condition, and similarly with manufacturing variability. With manufacturing variability, there are different things that we should think about, and these are for structural engineering, for instance, geometric, damping, material properties, the joint details, and the boundary condition. So in a nutshell, those are the things that we worry about. But now, why do we need something that is interpretable and explainable? Well, if we have to make decision making, basically, and we have to make decision based on uncertainties, then we need to be able to explain how we did that prediction. And actually, we have to interpret that, and we have to be able to communicate the prediction to support decision making. So interpretability and explainability become extremely important. And there's something that is almost hidden inside that. In a way, if we are able to interpret how a prediction was made, we will be able to understand. If we think about something that is explainable instead, we will be thinking about the fact that the prediction must be comprehensible and actually capable of quantifying what we don't know. Now, if we think of the importance of being interpretable, is because people will trust more something that they will understand. If we have a physics-based model, they understand how the physics-based model was selected, then there will be more confidence. But of course, there's another very important part, there is explainability. At the end, who is taking the decision are people. And critical decisions then need to be presented in a format that is understandable by humans. Okay, so what is the overall goal then? What does it mean having an interpretable, and intrusive uncertainty quantification approach? Well, what we would like to do is twofold. We would like to basically consider a physics-based model that is as detailed as possible. Every information that we have, everything that we know, we would like to be included. And then we will use finite element, boundary element, and expense it to evaluate models. And then what we would like to do is basically not apply any modification or simplification to the physics. Everything that we know, we would like to retain. We would like to account for uncertainties, taking all the information that we have available, and then look at the response metrics. And of course, it would be to say, okay, I want to understand the performance using few evaluations as possible, and having these results that I can interpret and explain. But of course, there are challenges in doing that. And I'm going to now describe to you which are the challenges in trying to do this and why machine learning is actually can be our friend in this and helping us enabling to do this kind of analysis. So imagine that we have to select the best performance design, and we are using a deterministic model, which is a structured system, in this case, a transmission system, and we run a physics-based model A, and we evaluate a response metric. Now we have a different design, let's call it B, and then we run the physics-based model. We have different competing design. We have Z of them. Great. What then we want to do is to select the best performance design. And it's the one that, of course, minimizes a performance metric. However, what happened is that this design can be obtained by parameterizing or considering completely different competing design. Now, what if we consider uncertainties? If we just take design A, so that's to Z, in design A, then we will have to include uncertainties. For each realization of the uncertain variable, we will have to run different physics model, and then we will have to evaluate the performance metric. But now this performance metric will depend on the fact that we have uncertainties. What is happening though is that pretty quickly we are increasing the computational cost. We are not just looking at design A, we are looking now, at design A and the uncertain design A, and then we'll have to do it for design B, design Z, and that it can be very, very challenging. And of course, the performance metric will change as well. Okay, so what does it mean? Apologies, sometimes there are new people arriving, so my screen does disconnect. Apologies for that.
Please ignore that. I can take care of that. Yeah.
Thank you so much. So let's imagine that we now are in the design uncertainty space. And again, I call this design of engineering system in general, but it's basically thing that you can use also for material for any type of design. So imagine that you have competing design solution, D1, D2, D3, Dn, and then you have the uncertainties, basically. And of course, for each realization, you're going to have all of these different domains. And the problem is that you don't want just to be for an uncertain variable along the oblique line or being in one of the horizontal line. You would like to evaluate all of these models. And of course, this is very much time consuming, but you also have to think about 4 different problems. So the first problem is how do we describe uncertainties? I told you which were the uncertainties. I haven't yet told you how we're going to describe them. And in principle, you can have 2 different types of uncertainties, parametric uncertainties and non-parametric uncertainties. What does it mean? Parametric means you take your Faraday model, for instance, the one of the card that I was showing, and you assume that you have some information about the physical parameters, and you describe that with probability density function. Then what you want to do is propagate the uncertainties, for instance, with Monte Carlo, and you want to compute the effect on the response. And in this case, the effects would be then captured by statistics of the response, confidence levels, and reliability. A non-parametric approach is something different. What it's saying is that you don't need to specify the parameters that are uncertain, but you can take uncertainties to an high level. And these are approaches that are used in vibroacoustic, especially for statistical energy analysis and random matrix theory. And they enable you to reduce significantly the computational cost. But they work under some assumption. Okay, so if we say that we then have to choose parametric because we are in the domain in which parametric is the only way forward, then we have to account for two types of description, probabilistic and non-probabilistic. What do I mean by that? Probabilistic means that we have information about some input parameters with a probability density function. Non-probabilistic means that we have just upper and lower bound, a region in which the parameters will actually live. Okay, but now what's the catch? Well, if you choose a certain uncertain description, you have to then use a certain uncertain probability. If it is probabilistic, you can use Monte Carlo, form, and other approaches. If it is non-probabilistic, there are other techniques that are well established. And of course, you can be in the case in which you have combined description. Now, the interesting thing is that it is not only the propagation that is changing, but also the results, how you describe the outputs. If you have probabilistic description, your results will be statistics, confidence level, reliability, and I'm assuming many of you are very familiar with those. And with non-probabilistic, there is the bounds on the responses that we are interested in. And if it is combined, then we look at the bounds on statistical results. Now, as I told you, what happened though is that if we change the description and we change the output, also the metric, the performance metric will change. Now, if we imagine that we have a probabilistic description, we will have at the end, for each design solution, a probability density function. And each curve will represent the response variable of interest. Then we will look, for instance, of what's the probability of exceeding a certain threshold, and we will look for the solution that actually minimize the probability of failure. That's pretty straightforward. That's what we most of the time do. But most of the time we have a problem. We don't have enough information to define a probability density function. We actually have, most of the time, just tolerance value, plus minus, for instance, the Young modulus, plus value, plus or minus the thickness of something. Or maybe you ask an expert and they can give you information in terms of plus minus what the variable will take, value will take. Great. There could be also other reason to use this sort of bounded description, because maybe you know that there are some physics-based limits. And so you know that the variable cannot take certain values basically. So if before we had a probability density function, now what is happening is we don't know enough. Not knowing enough means that we may change the probability density function as input. But the performance is strongly dependent on the PDF. Now, another thing that is very important to say is that an interval, a tolerance value, is not a uniform PDF. And by that, I mean that if we say there is a uniform PDF, we will be adding information. Because now each value within the interval has an equal probability of occurring, and there will be also very low probability of random sampling at the bounds. And it may be that at the bounds we have some information. Imagine this in the multispace, of course, as well. Okay, so this is the fourth problem that I was trying to describe. And I told you that there's something about the metrics that is changing, because now we have bounded. We don't have any longer PDF, but we have bounded descriptions. So for design A, design B, design Z, we do the full propagation and we get this. And now the metric of interest is changing, because it can be the minimum of the upper bound or of the lower bound. Okay, but then how do we handle this? How do we handle the fact that we have to take into account uncertainties, and how do we reduce the number of simulations if we want to then to use it to compare design? Now, let's assume that you have a detailed deterministic model of the engineering system. If you have intervals, that will be given as an input. You get an uncertain output variable that depends on this input parameter. What it means is that you will have each of these gray curves, there is one realization. And then maybe your performance assessment is the response within the bounds, these blue dots that are shown in the figure? If it is, then I'm satisfied with that. If it is not, then that's not the design that I'm going to use. Okay, what's the main problem? That in principle, we should calculate our response variable for every single value of B. And this is remembering that we have an expensive to evaluate model behind it. So most of the time, we will be able to calculate the response at a few points, but not exactly at every point. or we will not be able to run anyway a model at those points. And what makes things even more complicated in case of interval is that we gotta have this expensive to evaluate model that has a non-monotonic response, which means that the upper and lower bounds of the response will not happen at the upper and lower bound of the variables. We will have also many uncertainties, and we have usually, especially in engineering, a limited computational budget. So how do we handle this? Can we solve this problem? And again, this is where machine learning can help us. And helping us in this case, not by looking at data that are coming from measurements, but actually looking at physics-based model that we can really take advantage of. Okay, so just to give you a quick overview, at the moment, what we do in this case is to look at vertex method. So we just look at the upper and lower bound and we combine them. And then we can look at the subinterval method. And of course, there are lots of global search algorithms. It's becoming an upper and lower bound optimization problem, of course. And depending on the assumption that you make, you can have different solutions. If you think about the global search algorithm, these are the most used. They require a reliable surrogate model. But there are problems with building the surrogate models. Imagine that you have to create this surface, right? And you want to create this surface because then you want to build this surrogate model to speed up computation. Now, when you have to use basically this observation with the surrogate model, you have many techniques that you can use. You can use polynomial models, you can use Gaussian process, artificial neural network, support vector machine. So there are many ways in which we can handle this problem. However, what is happening is that when we try to build the surrogate model, we have to remember what we have. So we want to have few simulation runs. So let's imagine that we can run only 4 full simulations of a multi-physics problem in which we have everything that we care about. And now we have our response, W, calculated K1, 3, 5, and K upper bar. So 4 points. Okay. Now, approximation, we can say, okay, it looks like this. Actually, we look at our model, we make it more complex, more complex, more complex. And then basically, what we see there on the left is our approximation with just 4 points. But of course, our approximation with just 4 points may not be representative because we don't have enough information about what was happening. What you see to the right, in fact, are the 330 model evaluations. So the black curve is what we don't know, and is what happens if we run 330 times models. Now, this is now telling us something from what we have to the left. Indeed, we will need information and more data. But of course, what is happening is that when we think about the data, we have to think about which is the right surrogate model, are we underfitting or overfitting the problem, how to tune the hyperparameters, which are the convergent criteria, how to select the training points. And actually, that's where we are coming in with this approach that I'm finally going to present to you, in which we say we find basically a way to select the minimum number of simulations that you need in order to get the upper and lower bound. What I mean by upper and lower bound in this case are this red cross that you see here and this blue cross there. So this is the upper, this is the lower, and that's the only thing that we care about. We don't care about getting a pretty response surface. What we care about is getting accurately the maximum and the minimum of the performance. Okay, so what is the proposed strategy in a nutshell? And where is machine learning coming in? Let's say that we have this interval as input parameters, and we just run a few complex model simulations, say 4 or 5. Then we build a response surface that actually includes the uncertainties. But this uncertainty is not coming from the interval. These uncertainties coming from the fact that we haven't run the simulation. And then what we want to do is to use function for selecting, which is the new runs that we should actually consider in order to improve the maximum and minimum prediction. And then we can do this iteratively. And of course, we can obtain, for instance, the maximum or the minimum of the response, but we don't stop there. we want to also quantify, which is the remaining uncertainties, that is coming from the fact that we haven't run all the simulation. And we want also to figure out basically a way to assess if the bounds that we get are satisfactory. So basically, the whole goal is to say which is the minimum number of simulation that we need of our physics-based model that we can consider as a black box because it's sitting, behind this machine learning algorithm. And what we're trying to do is to get the maximum minimum of the response, but also quantify the uncertainties caused by not having run all the simulations. Okay, so if so far things make sense, and I hope that this step-by-step introduction helped you. Now we can dive in on the actual technique. And the big shift that we have to do is to go from a continuous function of the response to a discrete response function, and account for the fact that we really don't know the response at those points in which we ever run the simulation. We cannot even guess. So what can we do then there? We can take our response function and let's call it now W vector, and we can take the response of B1, B2, Bn, whichever is the combination of the B vector that is the uncertain input parameters. And now we account for the fact that at some point we ever run the simulation. Now, what we can say is that if we ever run the simulation, so if we don't have the simulation results W, a B something, then that is going to be uncertain and is a Gaussian random variable. Now, what this means is that at the end, we will have a collection of Gaussian random variables. So at every point, let's imagine that we didn't run any simulation. At every point, we have a Gaussian random variable. The collection of these Gaussian random variables is a Gaussian process. This is now enabling us to move into a setting in which we can leverage the physics and using machine learning to select simulation. How does this work? We take this W vector and we divide it in two parts. And the first part are the noise-free observation. These are our simulation. We run them. We know the results. And then the W star K, there are all the points in which we want to predict our response. So those are function realization in which we haven't run the simulation. So when there is this little person here thinking. And what we want to do is to get the response there. Okay. So what we can do then is to use a GP regression model. That is this non-parametric approach. Okay, how does it work? Basically, we take the noise-free observation and the function that we want to predict, and we say that jointly they have a Gaussian distribution. Now, Gaussian processes, regression model have been around for a very long time. There's a very great book written by Rasmussen and Williams, so you should definitely go there for finding out more about it. And basically what we are saying is that we have mean and we have to define what is called the variance. Because it's a Gaussian distribution, we need two moments. And of course, we can talk about the covariance matrix. And the way in which we describe the covariance matrix for a Gaussian process is by using what is called a kernel function. So most of the time, we say for the mean in the prior assumption that is zero mean. And then we make an assumption, though, a strong assumption sometimes, on the kernel function. And that, in fact, encodes the smoothness of the response function. And basically what it does is that it gives you a value that says how similar are the response obtained, how similar, the term similarity is basically between the 2 points. Now, this is the key assumption that we have to make, and there are several that you can use. And sometimes when you don't know anything, there are also kernel functions that you can use. And again, this kernel function look at the smoothness of the response that you haven't run. But what's the powerful of this? Because we are dealing with Gaussian processes, then by conditioning, we can calculate basically the expression in closed form of what is the probability of basically observing a certain value W star. Now, this is by conditioning that we obtain this, and it's basically a predictive marginal, a predictive distribution. But we can also look specifically at what we care about. There is the predictive mean and variance. At each test point, again, this test point is where we haven't run the simulation. And again, if you look at the book in Gaussian process, you will find this expression. They were there, simple calculation, you can do it by hand. And what I'm going to show you in the next slide is just an example of how we can use them. So let's imagine that we have this function here, and basically it's our unknown true response. It will take 330 simulations to obtain it. If we take just the upper and lower bound of the response, we will actually underestimating and overestimating the upper and lower bound, as you can see here, because the upper bound is here and the lower bound is there. Great. So what do we do with the Gaussian process? Let's say that we select 3 points only, and this is our training data set. We use this expression to obtain the red line, there is the mean, and then we have this gray area, there is the 2 sigma, there is the variance. Okay, so the confidence bounds to be precise. Now, of course, the more red dots we will add, the better the approximation of the response will be. But to be honest with you, we don't care about that because we can run only few simulations. So what do? We don't need to have an accurate surrogate model for every single value of k, but we can look locally. And something for those of you that are very interested in Gaussian processes, these are the parameters that were used. And of course, when you have the Gaussian process, depending on the kernel that you choose, you will have also to tune the hyperparameter. Okay, so this is our Gaussian process. But now, how do we get better? How can we select which is the next point, the next red dots, that will enable us to get as fast as possible to the maximum value? So the way in which we do this is to exploit what is called Bayesian optimization. And Bayesian optimization has been around for a long time. There are some, you can find some in this reference, some brilliant reviews about what has been happening. But basically, what we are trying to do is to exploit this Bayesian optimization and to add some flavor to it, to make sure that it works for what we care about. So our goal is to look at the next simulation, and I'll encourage you to focus on only the red vertical line. Remember, we don't know the black function. That would require 330 full simulation. We don't want to do that. We have only 3 at the beginning. And we have the red curve, and there is the approximation, the mean approximation, and the vertical line. There is where now our Bayesian optimization is telling us to go and sample again. So it's very close to the first point. Then we go and we get the point, and we get this green box that you see here. Then we ask again, automatically, of course, to go and look for the next point in which we should sample. And will give us basically this other point here, this green point there. Okay, so we run the simulation. So basically it's telling us, so we have at the moment these red points and the green, and it's telling us to sample here. We sample there, and then it's telling us automatically, iteratively, where to get the next point. Now, remember, we don't know anything about the system, and this is happening automatically in the background until we reach a certain iteration number. So how did the code decide this? How did Bayesian optimization work in the background? What was doing was using what is called an acquisition function that is telling us where to acquire the next point, where to get the next simulation, in this case, for getting the max. Okay, how does it work? It takes the observation that we have up to the point, and again, observation are results from physics-based simulation, our W0, and basically say, okay, from those, I can look at the max. So for instance, in this case here, the max will be this point. Okay, this is the maximum observation that we have up to the point. Now, what we can do is to look at improvement. Improvement means, can we improve with respect to the current max? Can we have basically our function to be greater than this max? If so, we will improve. Otherwise, we won't, because we are looking just at the max. Now, there are different ways of doing that, but basically, the gist of it is the following. So if you define improvement in this way, now we want to talk about probability of improvement. And these are deterministic values that you got, but this is coming actually from the model that you've just approximated. We just took our WP and we say, okay, wait, we can use a Gaussian process. So if this is a Gaussian process, then this is a normal distribution. What it means is that we can then, again, very easily go through it and calculate the probability of improvement. How probable it is for us to improve. And it's expressed in this way, and again, it's a Gaussian distribution. But also, what we can look at is what is called expected improvement. And what this function will do is actually balance what is that we know and what we want to explore. So if we know something, we say that we exploit what we know. And if we want to go farther away, we say that we explore. Now, the probability of improvement is one of those acquisition functions that actually uses mostly what we know already. While the expected improvement is very good at balancing what we know and what we want to explore. Okay, so perfect. So now the problem is that I explained to you what's happening in the background, how to select the next point simulation, but when do we stop? How do we select when we say enough? Those are enough simulation. Again, we don't know the black curve, so we cannot really say, okay, now we stop. Okay, so in principle, let's say that we have an iteration number 0, these points that have been suggested. Again, let's focus on the vertical red lines. Then we get this point, and we now say being told to sample here. And we can look at iteration 4, but we can look also at iteration 7. I mean, they both look pretty good, and they get actually pretty quickly onto the maximum. But how do we stop? So one way to stop, obviously, is to say, I have this much simulation, and so then I need to stop. But of course, there's another criterion that can be used. And this criterion is to say which is actually a value on the acquisition function that is reached. And one of these is usually to say which is the maximum value that the acquisition function will take. If it is below a certain value, so for instance, in this case, 10 to the minus 2 for the expected improvement, then we say we stop. Okay, so if we say so, then we can actually stop our simulation. But how do we know if the bounds are satisfactory? Well, I can start writing a question for you, and I can go through them, but probably will not be very helpful. But what I can tell you is that one way to do that, and that's where we also contributed, was to say, how far are we going? So with our acquisition function, where is the acquisition function suggesting us to take the next point? And how far is with respect to the current optimum? Another metric that you can think of actually saying, look, if you look at the current maximum or minimum of the observations, which means the simulation that you've run, how far are they from the current optimum? And if you look at these two types of conditions that we have there, then basically what we can say is that if they are not met, we actually have to run more simulation. We haven't got there. We haven't got to the actual bounds. And this can help us reduce potentially large inaccuracy. Now I'm going to show you in a few minutes an example for that. But just to give you, then I know that I was giving many inputs and many information, but how does it really work? So imagine that you have your physics-based model, you have these uncertainties, and you start selecting just few simulations to run. Then what you do is that you build a GPU regression model, and you use every single data that you have. Then you check if you need to stop simulation. It can be that you're already getting the maximum, for instance. And then you select, in case the stopping criteria is not satisfied, you select one simulation needed to run for improving the upper bound. You run the simulation, and you have a new training data set that now contains the point that you had at the beginning plus this one. And then you go back and you build the GPU regression model. And again, you go in a loop. So it's an iterative loop. Once you then get the stopping criteria, you actually get out from this loop and you get the response, but also you check the metrics. Now, in a very Bayesian optimization fashion, you can do this by considering the upper bound separately from the lower bound. And we can start with the same GP at the beginning, but then we will have two different enhanced training data sets for the upper bound and the lower bound. What we argued is that it could be actually, in some cases, and we have observed that, it could be a better idea to combine this information. So you start with some initial simulation, but when you select the upper bound and the lower bound, you select both on the same GP regression model. And then you enhance the training data set, not just with one simulation more, but with two together. And then you go back. And as a result, when you stop, you will get the upper and lower bound response. Okay, so what is happening now? I was talking about interval and how to use machine learning to get interval, but I ended up talking about probability. So how is this really working? And how can this be easily communicated to engineering? Again, we want to actually having an approach that is explainable, and I hope that I was able to actually explain it to you and interpret also what is happening. So can we actually, what can we do with this? So we were interested in the maximum and minimum of the response. And of course, the easiest way to see is that now this approach enabled us to select in a clever way points in which we will know that we are going to improve our maximum and minimum prediction. So we're just going to trust this deterministic observation. That's one way to look at it. The other one instead say, wait, but at each point, so say here, for instance, this is our current maximum of the response, very close to the green. We're going to have not only the mean prediction, there is this red curve, but we're going to have also a variance prediction, confidence bounds. So what we can do then is to say that the upper bound and lower bound are themselves interval variables. And then we say which is the actual upper bound is going to be the mean plus the uncertainty. And the lower bound instead is going to be defined in this way. If we say so, what is happening is that now we are always going to be able to overpredict the upper bound with respect to the current simulation results that we have. And we will always be able to underpredict the lower bound. And what is this? What does this mean? Is that we are always going to be better than the actual physics-based information that we have, and we will be always overconfident with respect to the physics-based simulation, not necessarily with the true response. That's why the metrics are so important. Okay, so I show you how the procedure works, but how does it work if we consider two separate enhanced training data sets? So this method A. If we look at the lower bound and we try to calculate therefore the minimum, we start with 3 points. That's where the acquisition function is telling us to go. Then at iteration 5 is actually going in the right direction. Iteration number 10, we're pretty much there. If we look at the upper bound, then we can look similarly at then iteration 0, 5, and 10. And you can see how it is going, but also how it was exploring other points that were far away from the max, just to make sure that things were going the right way. In order to do that, we needed, so instead of calculating 330 simulation, we just needed 20 of them. 3 initial, 12 for the lower bound, 7 for the upper bound. And what we did to stop was saying if the acquisition function, that was expected improvement, is below this 10 to the minus 2, then we will stop. So that's how the code decided to stop. And again, 20 simulation versus 330. Again, the results that we will get are going to be physics-based. Okay. And then if we instead consider this combined approach in which we account for the same GP, but we look for the maximum and minimum, these are actually all the results that I've been showing to you up to now, because up to now I was always showing to you figures in which we have this red and this blue. And again, the red is telling us where the acquisition function wants us to go to improve the max, but the blue is telling us where the acquisition function wants us to improve the mean. So in this case, it was saying we start from these 3 points. You should look at here, you should look at this for the next point. We run the simulation and then we are here and there. Again, the acquisition function, apologies, select that and is building the response. What you can notice from this is that because we are at the same time looking for the max and the minimum independently, we are also getting for free a better approximation of the entire response surface. And in this case, in fact, we are able to reach to basically to reach the tolerance on the acquisition function of the expected improvement in only 14 simulations. So in this case, we reduce even more the number of simulations that we needed in order to get the response. Now, just to give you some information, because I'm sure that many of you will wonder this. I started with 3 points. What if I was having as a starting point 6 points, 9 points, 12 points, 15. Will this get better? And what you see there is the total number of simulation for initial training data set. What you see here is the percentage error. In the left is for the lower bound, and in the right is for the upper bound. And what you can notice is that not necessarily improving or including more points in the initial training data set will give you better upper bound or lower bound. Not for method A, not for method B. The reason is pretty simple, because with method A and B, what you're trying to do is to select the point that matter the most. While if you just, in this case, we took equally spaced data points, those information give us maybe a better response surface, but not necessarily a better approximation of the maximum or the minimum. Okay, and just to give you another sense, that was a very simple, 1D case. I can show you a pretty picture. That's nice. What if we go higher in dimensions? So in this case, we had a physics-based model. It was taking a couple of hours to run, and we will have 4 uncertain parameters to consider. And this is a typical vibroacoustic problem that is found to provide some insight in the structural acoustic domain. So what I just wanted to point out to you are what we did for validation. We used this subinterval method, and we had to run this very large number of simulations. If we use just the upper and lower bound, we need to just run this. Now, this is our, let's say, true response. And if you look at what happened if we just take the upper and lower bound of the variable, I mean, for one, it's going to be okay. We're going to get 0%. But for the other one, instead, we get an error that is 56%. We show this because sometimes a bound can happen also at the upper or lower bound. And it's important to remember that. And then what we can show to you is what happened with approach A and approach B for the upper and lower bound. And what you can see here, I don't know what is happening. Sometimes things are appearing. Apologies for this. But if we look at approach A for the lower bound, we will need just 12 simulation. If we look at approach B for the lower bound, we will need this at 29. But for approach A, we actually spot on the value. And in fact, we get 0 error percentage. For approach B, instead, we have an error. What is important to notice is that when we get this value, we also get an uncertainty. So in a way, we have a flag. We have something that is telling us, look, that is actually not the right value. And actually, if we look at the observer or the values that we have already run, we add this value there. Okay, so then if we look at the upper bound of the response, we can do a similar analysis. We can use approach A or approach B. Remember, approach B for lower bound and upper bound are actually happening simultaneously. This is just for simplicity shown in this way. But in order to get a good approximate solution, we will need to run this many analyses with approach A, much lower with approach B. But you can see here that we still have a small error. And in principle, here we will see that the uncertainty is 0. However, you can see that there are things here that are different. So it's a small variation in the position. And actually, most of the condition will not be met. And in fact, for the lower bound, we will need to run one only additional simulation. And also for this case, we will be actually given, in this case, exact values because we get the upper and lower bound, but we will be flagged that there is a small variation. Again, the metrics do not know which is the percentage error. They are based on where the acquisition function is telling us to go and where is the prediction of our bound with respect to what we have evaluated up to the point. Okay, so again, this problem is bigger. We have lots of uncertainties. What happens if we change the initial training data set? If we look at 8, 9, 16, 25, you can see again that the number of points do not necessarily give us a better error, reducing error. So we don't reduce the error in the prediction. Okay, so this concludes my presentation. And what I showed to you are 2 non-intrusive approaches, and they drastically reduce the number of runs required. And they enable us to also quantify the remaining uncertainties. And the good things about this is that they are interpretable, explainable, And if we think about interpretable, we have behind it an expensive to evaluate physics-based model that is as a black box. We use a Gaussian process to embed what we know and what we don't know. And what we know are these noise-free observation, and what we don't know is actually partially know, actually we can say, is the kernel. So we can embed also the user knowledge. We also are able then to select simulations that are justified between the trade-off or exploiting what we have and exploring the domain that is uncertain. And we get a bounded description of the response bounds, and we have metrics that verify if these bounds are satisfactory. And the good thing, and I would like to stress this again, is that we are always going to be over-predicting the upper bound and under-predicting the lower bound with respect to the current observation. Of course, it's not that we solve everything. It's not that the world is perfect now. There are still many challenges in the field. And one of them is related to the GP that is very robust up to 20 dimension. And therefore, how then you combine mixed type of variables if you have probability function and intervals, how you combine them with experimental data, and if you have continuous and discrete variable, how can you choose better acquisition function, and many more. So without further ado, I would like to thank all the people that worked with me, and in particular, Filippo Giunta, that actually was my collaborator for this paper. You can find all the data that I showed to you in this paper. There is open access. So thank you so much, and I will be extremely happy to take any question you may have. Thank you.
Thank you so much, Alice, for the wonderful talk. We do have two questions posted in the Q&As in chat room. The first question is from Dave Brown. He asked, how does this system work with multiple dynamic models? For examples, the engine generates different torques at various RPMs, and there are competing concerns of heat generation and fuel economy. The designer needs to not only evaluate their designs, but review options to ensure that the best choices are made in selecting among the various design options. In short, can this be used to do predictability of the best more than one of the balanced options in the optimization?
In principle, it can. Also, if you take just one design, it can tell you for that design which will be the upper bound and lower bound performance. Of course, if you then want to select design, it depends also how you define each design. Are they parameterized? Are they discrete variables? Can they be seen as discrete variables? Are they categories? It's a continuous parameter space. So in principle, it can be, but it really then is dependent on the problem that we have attempted. But everything that is in the physics behind will stay as it is. I don't know if this answers the question. Maybe.
Yeah, I think it does. Okay. Dave, you want to comment on that? Okay, let's move on to the next question. The second question is from Rob Hayes from NC State. He has the upper bound points did not appear. Okay, so he's talking about slide 33, by the way.
Yeah.
So if you go there, so he asked, the upper bound points did not appear equivalent to the lower bound points being fitted in that the upper bound fits enjoyed data at the corner locations where the derivative is discontinuous. Can you explain whether this is correct?
Yes. So, okay. So if I understood well the question, there was some problem with the audio, so apologies in case I didn't. It's about the upper bound being this sort of smooth value, while the lower bound being a very basically sharp corner, let's put it this way. Now, the thing is that we are seeing this. This is, to be honest with you, what is behind it, if you want to know. It's a single degrees of freedom. So it's a very simple model. And because of the resonance, you see this kind of effect. And it's driven out in the time domain, basically. We are looking at the peak in the time domain. And what you see there, it's something that can happen. And we chose this case study because it was also very complex. And the kernel function that we have is not the one that accounts for the fact that we have sharp corner or smooth corner. It's actually the one that says, okay, you know nothing, so what do we do? So in principle, if we choose, or if we knew already from the beginning what was this behavior, we could attune this better. Now, if you look at the top, we start with these 3 dots, and then the blue is actually telling us where to go next. And you can see that at iteration 5 is learning where to go, and then it's actually still going to the right because it's understanding that it's going low, but then it figures out that it has to go back. So in this way, then it's able to go back to this sharp corner. Similarly, what you see instead below is that you start climbing, and at iteration 5, we are actually almost at the top. But then, because there is so much uncertainties in the rest of the domain, it actually pushes to the rest of the domain. I hope that if I understood correctly, answer that these answers sorry, if I understood correctly the question, that I understood that I gave the right answer. Or maybe we can talk about this offline.
Yeah, that sounds great. All right, the next question is from Xiaoting. She has a question about slides 35 and 38.
Yes.
And she asked how to interpret the needed number of data points. Is D9
Yes.
good?
Yes. So basically what you see here is D3, D6, D9, D12, D15 are the initial training data set. So we basically take this interval and we say, okay, do we take just 3 points? Do we take 6 points? So we take the interval and we divide it to get 6 points out of it. We divide to get 9 points. And of course, these are equally spaced data points. So there's nothing fancy behind that. And what we wanted to try to see was that if we added more points, and of course we could have done it, by randomly selecting points as well, but we wanted to have some control. Would we, by adding more points, would we get better results? So what this is telling us is that for D3, in order to get to the accuracy level on the expected improvement, we needed 17 simulation for the lower bound. And actually, in this case, apologies for approach B. And then if we look at this instead, we will need 20 simulation in total. So this is looking at the lower bound and upper bound combined. And in fact, is what I showed you earlier when I say, you will need just 20 of those. And then for the other one, instead, we needed less. And this is the results that you see here. And if we add D6, you can see that it's going lower. But what I wanted to show you then was not just the number of simulations, the fact that the total satisfy the expected improvement was different, but also that the percentage error is actually changing. And in fact, even if you have a larger number of simulation and you have a large number of data set, you can still get an error that was actually bigger than the other one. So this is how to interpret this graph. I know that they contain lots of information, but yeah, this is the total number of simulation for each of these. Then we look at the error by comparing the actual bound with the bound that is going to be predicted. And you can see that anyway, in terms of percentage, there are very small differences.
All right, thank you so much, Alice. Okay, that was all I had in the chat room. But is there any other question from the audience? Then you can unmute yourself and ask question directly. I have a question or rather comments. I mean, I'm working on the reducible model, the project and the sampling. Efficient sampling procedure is really key there, as you addressed in your talk. And the Bayesian optimization type of the sampling method has been applied in reducible model community as well. However, as you mentioned at the end, the upper bounds is like parameter 20 parameters, and above that, we still need a more efficient sampling procedure. Do you have any insight or how to address that challenge you listed as one of the...
we are trying for the high dimension to look at ways to combine different Gaussian process results. So basically, how to we see this as a two type of problems. Of course, you can start looking at the sensitivity analysis of the variables, and therefore then try to look at those that are sensitive and reduce the dimensionality from at least partially, and then look at projection scheme in which then you look at the different GPs. You basically optimize the different GP, but the problem then what we're seeing is of course combining these different GP in a meaningful way. So this is actually something that we are definitely very interested in and looking at. For us, also the other part is really this combined PDF and intervals, because most of the time the inputs that you get are, for some variables at least, are described from PDF and intervals. And it is not at all clear then how you can do that, because usually these PDF, of course, are not Gaussian, but they are coming from different probability density function. But I would be very happy to follow up this with you or with anyone who's following the talk today and discuss further about this.
Yeah, in terms of the Gaussian process, the point of contact at Lawrence Livermore, who's doing the Gaussian process research, is the one person I know is Jason Bernstein. He was here, but he left because I guess he has another meeting. I can connect him with you, and I can also follow on this matter with you as well.
Yeah, that would be awesome. That would be
Yeah. Right. Okay. Well, with that, I think we can conclude. Thank you so much for the great talk, Alice. Let's thank our speaker today. And I hope that this talk will initiate further collaborations between the Lawrence Livermore and your group, and as well as other external, the audiences who joined us today. Thank you again, Alice, for the wonderful talk.
Thank you again for this, for giving me this opportunity. I really enjoyed it. Thank you so much.
Yeah, you did a good job. Okay.
Thank you. Bye bye. Have a good day. Have a good